When we talk about reaction rates, the rate of a chemical reaction can be defined as the amount of reactant that vanishes or the amount of product that is produced as a function of time. So we start our reaction and we can measure as a function of time, as I say, the concentration of either the reactant or the product, and this is defined as delta of the concentration over dt, or as in the infinitesimal limit it's dc dt, where dc is the small change in concentration and dt is the change in time. And what we can then produce, if we do our experiment, a concentration versus time graph, where this could be, for example, the decay of reactants as a function of time. And what we really want to do is we want to be up, because you can see that the slope changes with time. Here it's very steep, here it's more smooth, and down here it's practically stationary. So what you want to be able to do is calculate the infinitesimal derivative, essentially, as a function of time. So at each point in the graph you can get an infinitesimal specification of the rate. And the steeper the slope, the greater the rate of consumption of the reactant. So here's an example where we have the Haber process. It's the reaction of hydrogen and nitrogen over an iron substrate to produce ammonia. And this is the chemical reaction, which is N2 in the gas phase plus 3H2 in the gas phase gives 2NH3. So if we're measuring the rate of formation of ammonia, then we can also determine the various other constituents just based on the mole ratios. So if the rate of formation of ammonia is 1.2 millimolar per litre per second, the rate of consumption of hydrogen is just going to be 2 over 3 times 1.2. Okay, so we can develop some rate laws based on essentially empirical observations. So these aren't things that can be derived from fundamental theoretical perspective. They're observed rates. And what was found was that the rate of reaction is often found to be proportional to the molar concentration of the reactants raised to some simple power. So this makes sense if you think about it, because you could imagine that if we have a reaction A plus B goes to C, we've got two reactants and they have to combine with one another to undergo some kind of chemical reaction to form the product C. And it makes sense when you think about it that the concentration would be important, because the more molecules you have of A and B, the more likely an A molecule is to find a B molecule and therefore react to give C. An example of this, and this isn't the only example as you'll see, could be observed to be some rate constant multiplied by the concentration of A multiplied by the concentration of B. Now up here we say that it's proportional to the molar concentration of the reactants raised to a simple power. In this particular case the power is just 1. So the rate is equal to K times A to the power of 1 times B to the power of 1. And K is a rate constant. So the rate constant is independent of concentration, which is good because concentrations will change during the reaction, but it's not independent of temperature. So now I'm going to go a little bit more into what reaction order is. So before I said that the rate of a reaction can be proportional to the concentration raised to some power. This is called the order of the reaction. So a reaction rate that looks like this, where the rate is proportional to the rate constant times A squared, is second order in A, because A is the species that's raised to the power of 2. It's also second order overall, because the way that you define the overall rate of a reaction is to sum up the orders of all of the components. And so, for example, in this reaction which we spoke about first, where we had A plus B going to C, the order is first in A because it's raised to the power of 1, first in B because it is raised to the power of 1, and it's an overall second order reaction. This is where we have to start to be careful. I've given a general rule. The rate of a reaction is often found to be proportional to the molar concentration of reactants raised to a simple power. Now that is just a general rule, and we don't say anything about what the simple power is. We don't have any information about that. What we'll find is that it's very difficult to determine what that power is. This states that the rate law is established experimentally and cannot in general be inferred from the chemical equation of the reaction. This is just to show that the rate of formation of the product here, HBr, has a very complicated rate equation. So what you see here in no way indicates what you're going to get here.